Hello everyone. The title of this video is determining the maximum and minimum values of quadratic functions. Now every example I'm going to be doing in this video is taken directly from a free online textbook at openstacks.org, and I'm in their Algebra and Trigonometry text, section 5.1, called Quadratic Functions, and I'm under the heading determining the maximum and minimum values of quadratic functions. Alright, so each example I'm doing is either going to be an example from the reading or one of the try it problems from the reading or one of the exercises at the end of the section that's related to this particular objective. Alright, so the first examples I have written out here. We're asked to determine whether there is a minimum or maximum value to each quadratic function, find this value, and axis of symmetry. Right. So remember parabolas, quadratic functions, the graphs are parabolas. If the parabola is opening up, right, if the parabola is opening up, then the function has a minimum value. I'll say a minimum y value. Right? When they're talking about the minimum value, maximum value, they're talking about the y value, the output. Because there is no highest x value, there is no lowest x value, right? The domain is all real numbers for quadratic functions. So when we talk about the minimum value of a function or the maximum value, we're talking about the y coordinates. Right? And notice there'd be no largest y coordinate, right? The graph's going up, would be going up forever, so there's only a minimum. And this is kind of separate from the example. Now, if the parabola is opening down, then the function has a maximum value or a maximum y coordinate, highest y coordinate. Right? And notice that this maximum value and minimum value, these occur at the vertex. So the key to all these problems is going to be finding the vertex of the quadratic function, the vertex of the parabola, which, based on previous videos I've gone over, you should know how to do by now. Alright, so here we're given a function, in example 1, y equals y of x equals 2x squared plus 10x plus 12. This is in that general form, ax squared plus bx plus c. Remember, the lead coefficient, a is 2, that's positive. And if that's positive, the parabola is going to open up, right, like this. That means this function, right, y of x, has a minimum value. Has a minimum value. Now what we're asked to do after that, is after you determine whether there's a minimum or a maximum value, does it open up or down, right? Then we're going to find that value and also the axis of symmetry at the same time here. Now, I've also brought this up in previous videos. If you have a general form, ax squared plus bx plus c, we know a is 2, b is 10, right, the linear coefficient. Remember, the axis of symmetry, that line that the vertex is on, that line that cuts the parabola in half, if you want to think about that. Right, so like if these dotted lines here, right, it's a vertical line that goes through the vertex. I'm going to be abbreviating this for the rest of the video as AOS. So if you recall from previous videos, the axis of symmetry, when you're given a quadratic function in that general form, is simply x equals the opposite of b divided by 2a. So here that would be the opposite of b, negative 10, divided by 2 times a is 4. That's negative 5 halves when you reduce it, right? And this is the x-coordinate of the vertex. So then the y-coordinate of the vertex is just simply plug this in. So what's y of negative 5 halves? Negative 2, plug in negative 2 and a half. And we get 2 times negative 5 halves squared plus 10 times negative 5 halves, and then plus 12. And we simplify, right? This would be 25 fourths times 2 would be 25 halves. This is minus 50 halves. And then plus 24 halves, right? Just getting a common denominator because you need a common denominator to be able to add or subtract. 25 minus 50 is negative 25, plus 24 would be negative half, right? Negative 1/2. This is the y-coordinate of the vertex, right? Which would be the lowest point on the graph, and this, negative 1/2, would be the minimum value of this function. Right, the minimum value of this function called y. And I already found the axis of symmetry. It's x equals negative 5 halves. So there, I've answered both parts. Well, actually all 3 parts, right? I said it has a minimum because it's opening up. Found the axis of symmetry, x equals negative b over 2a, negative 5 halves, and then plug that in. You get the output, which is the y-coordinate of the vertex, and that'll be the lowest. Now, if you want to verify this, let's go to a graphing calculator to verify this. So I got a free online graphing calculator here at desmos.com, D-E-S-M-O-S. And I'm just going to simply enter the function they gave us, y equals 2x squared plus 10x plus 12, and look at the vertex. And you see how it definitely has a lowest point. And look at the y-coordinate of that lowest point. It's, well, let me label it. It's negative 0.5, negative 1/2, just like I said. The lowest value, the lowest y-coordinate, the lowest output reached by this function is negative 1/2. Every other output is higher. Right. And of course, the axis of symmetry you see is at x equals negative 2.5, negative 5 halves, which again, I said earlier, that was that negative b over 2a. Great, so got a nice graph here verifying my statements. All right. Okay, so next example, very similar. Once again, I'm giving a function in general form, y equals ax squared plus bx plus c, where a is negative 1, right? The coefficient on the x squared is negative 1. So this tells me, the function, the parabola, is going to be opening down, right? It's a negative lead coefficient, so like this. So the vertex will be the highest point, right? That means that this function, f, has a maximum value. Sorry, that's supposed to be an m. It has a maximum value. And we just need to find it. All right, and then b, all right, b, it's our, it's in general form here is 4. The axis of symmetry, be x equals, negative 4 over negative 2 is positive 2. All right, negative b over twice a, negative 4 over negative 2, positive 2. Right. And then I plug this in. Right, so there's another part they wanted, right? What's the axis of symmetry? And then f of x, well, plug in 2 for x. Get that. What's that maximum value? What's the y value, the output of the vertex? So the opposite of 2 squared plus 4 times 2 plus 3. This is negative 4 plus 8 plus 3. It's 7. And there we go. That is the maximum value. I'll just put max value. That's the maximum value of this function called f. All right, and let's verify that. Again, I always like checking my solutions. I don't do it all the time in these videos, but when I'm doing stuff on my own, as you should check your solutions, verify that you are correct, that it makes sense. Right? So again, going back here, graph the function they gave us, y equals negative x squared plus 4x plus 3. And you see it's opening down. There's the vertex at the point 2, 7, right? X equals 2 is the axis of symmetry, and the highest y value achieved is 7, right? That was what I said the maximum value of f was on the previous page. So it looks like we did a good job there. All right. Next example, more of the same. I guess the only difference is, it's a function of t instead of x, but you can change the t's to x's, right? The input of this function's called h of t. The input's t, the output is h of t, or just h. You can change this t to x if you want, if you're more comfortable with x's. No big deal. Again, the function's in general form, a times t squared plus b times t plus c, right? Just like ax squared plus bx plus c. So the value of a, the lead coefficient, is negative 4. Right? That means the graph of this parabola will be opening down. And if it's opening down, right, that means the function h here, h has another maximum value. Okay? And now we just need to find that, right? Alright, so the axis of symmetry. Same deal. I got a is negative 4, b, that's the linear coefficient in this general form, that's positive 6. And that'll be t equals instead of x equals. Again, if you want to change them to x, you can. Negative b, which would be negative 6, over 2 times a, which would be negative 8. So positive 3/4 when you reduce it, right? So t equals 3/4 is the axis of symmetry. And then I plug this in. What's the value of h at 3/4? And this will give me the output of the vertex, this maximum value of the function. So this is negative 4 times 3/4 squared plus 6 times 3/4 minus 1. This would be 9/16, but times negative 4 would be negative 9/4 plus 18/4, and then just to get a common denominator, minus 4/4, right? Minus 1. So that's negative 9 plus 18 is 9, minus 4 is 5. This is 5/4. And there is the maximum value, the highest y coordinate reached for this function called h. And again, let's verify this. Now, the nice thing about Desmos is you can enter functions of other variables. You just got to make sure you're using function notation, right? The h of t equals negative 4 times t squared plus 6t minus 1. And now, the horizontal axis is now, the t-axis, and the vertical axis is the h-axis. And look at the vertex, right? 0.75, right? Remember we said t equals 3/4 was the axis of symmetry, 0.75. And 1.25, that's 5/4 is the highest value, the maximum value of the function. That's exactly what I had written out here on paper. Okay, wonderful. Okay, next example. Same stuff. Again, we're asked, does it have a maximum or minimum value? And what would that be? What's the axis of symmetry? So once again, it's in that general form, and if I were you, I'd put it in general form. If it's not, get ax squared plus bx plus c. So the value of a here is negative 1/3. So again, we have a negative lead coefficient, so this is opening down, the graph of this parabola. It's going to have a maximum value. Right? So this function f will have a maximum value. Now we just need to find out what that is. The value of b, right, is negative 2. Don't forget the negative. So the axis of symmetry, remember, is x equals negative b, which would be positive 2, divided by 2a, which would be negative 2/3. Which, remember, dividing by negative 2/3 is the same as multiplying by negative 3/2. So this is just negative 3. All right. And you can also multiply the top and bottom by 3 and see that. You'd have 6 over negative 2, which is negative 3. So x equals negative 3 is the axis of symmetry. That's the line the vertical line that'll cut the parabola in half that runs through the vertex. And now I want to find the vertex, right? So or the output of the vertex, the y value. What's f of negative 3? It's negative 1/3 times 3 squared minus 2 times 3 plus 3. 3 squared is 9. A third of that is 3, so this is negative 3, and then minus 6. Oops, sorry, negative 3, so plus 6. My apologies. I'm plugging in negative 3 for x, not positive 3, but still, negative 3 squared is positive 9. That would still be negative 3 in the first term, and then plus 6. And then we have plus 3. Negative 3 plus 3 is 0. This is 6. All right, the maximum value that I'm looking for, I'll just say this, is 6. That's the highest value, the highest y value achieved by this function. And again, let's verify it. Going back to Desmos, and I'll put in that function they gave us, y equals negative 1/3 times x squared minus 2x plus 3. And look at the vertex there. See, negative 3, 6. X equals negative 3 is the axis of symmetry, and the highest y coordinate, the maximum value, is at 6, as I wrote down on my paper. Excellent. All right. So the rest of the examples I'm going to work on are from the real-world application problems at the end of the section. All right, so the first one I'm doing is exercise 66 from the text. Let's take a look at that. So going back to the text here, scrolling down to the exercises, and all the way to 66. Okay, here we go. And the first one I want to do is 66. It says find the dimensions of the rectangular corral producing the greatest enclosed area given 200 feet of fencing. Alright, so hopefully you can still read 66 here. So look at this. So what this means is I'll draw a little picture. You know, you're enclosing a rectangular area. Right, so I'll draw like a rectangle here. Here's this rectangular corral, right, with some fencing. Right? There's all this fencing, but you only have, 200 feet of fencing. Now, another way to say this is that the perimeter of the rectangle is 200 feet. And we'll use that. Perimeter equals 200 feet. We'll use that in a second. Now, just like any word problem, I read through it and I identified the unknowns, right? They want us to find the dimensions. Right? What do they want? What don't I know? Now, the dimensions of a rectangle are length and width. Right? So I'm going to call these something. Right? I'll call the length L, or you can use X if you want. It doesn't really matter. And I'll call width W, and it really doesn't matter if the length is horizontal or the width is vertical. So there's L, it's an L by W rectangle. All right. And what we're trying to do is find, after this, the maximum area. Right, they said that gives us the greatest enclosed area, right? Greatest enclosed area, maximum area possible. Right, because there are lots of different rectangles I could make. Right, so let me go back to my paper, make it a little bigger. Right, because if I had 200 feet of fencing, you know, I could do this. I could go 50 feet over here. Well, I could just do 50 feet all around. Right? There's 100, there's 200. And the area, remember area of a rectangle is length times width, right? Square, whatever, right? Feet in this case. So it'd be 50 times 50, 2,500 square feet, right? Feet squared, or square feet if you want to write out the word square. That's one possibility. Or, you know, what if I could do this too? What if I put 25 feet here, made the width 25, that'd be 50, and then I'd have 150 feet for the rest of it, so I'd have to go 75 and 75, right? And there's 200 feet of fencing, right, total. The area of this rectangle would be 25 times 75. That'd be 1875 square feet. Right, that's 25 squared, 625 times 3, yeah, 1875. So you see there's multiple possible areas I could make, right, depending on how I use the 200 feet. We're trying to find the largest area though. Now so far, 2500 is the biggest, right? You know, we'll see that that actually is the biggest in a second, but we're going to actually set up a quadratic function, right? So how do we do that? Right? How do we set up a quadratic function? Well, we're going to use the whole perimeter equals 200 feet deal. Remember, the perimeter of a rectangle is twice the length. Right? There's a length, width over here, length here, width here, length here. It's L plus W plus W. 2 lengths plus 2 widths equals 200. And if you divide everything by 2, that means L plus W needs to be 100. Right, and you see that in both my examples down here, 50 plus 50, 25 plus 75. No matter how you set this up, the length plus the width needs to be 100 feet. And we have down here area, right? Area equals length times width. Well, right now, the way I have this written, area equals L times W, area is a function of two variables, L and W. L and W. We're not used to this, right? We're not used to seeing functions of two variables. We want a function of a single variable, right? A quadratic function. So we're going to make a substitution. And here's what we're going to do. Right, take this here, this L plus W equals 100. Just solve for one of the variables. Say W equals 100 minus L, or negative L plus 100. And then substitute this 100 minus L for W in the area function. Now, the area, A, I'll use A for area. Now the area is L times 100 minus L. And after that substitution, we have a quadratic function of L. And you'll see when I distribute the L here that it's a quadratic function. So this is going to be happening in a lot of these real-world problems here in this section. You're going to be given certain information that you'll use to make a substitution into what you want to maximize or minimize. All right, and then after you make that substitution, the thing you want to maximize or minimize is going to be a function, a quadratic function of a single variable. And now what I want to do is find the maximum value of A. All right, watch this. So now we have A equals, and if I distribute the L here, that would be negative L squared plus 100L. Do you see the quadratic function now with L squared? So when I'm graphing areas, you know, the horizontal axis is going to be L's, vertical axis will be A's, right? Instead of, you can change them to Y and X if you want. Now from the factored form, I see that when L is 0, the output would be 0. When L is 100, the output would be 0 as well. And using symmetry, halfway between would be where the axis of symmetry was, right? And you can see little a would be -1, it'd be a parabola opening down. Little b would be 100. So the axis of symmetry would be L equals, -100 over -2 would be +50, right? L equals 50 is the axis of symmetry. And if I plug this in, we're getting negative, 50 squared plus 100 times 50, or just 50 times 50. If you go back to the factored form, that's 2,500. So the maximum area is 2,500 square feet. That's it's a parabola opening down like this. Now I wouldn't actually go below to the negatives because these are talking about areas. Areas shouldn't be negative, but this is it. This is the maximum. And they asked us for, what are the dimensions? What are the length and width? So, the dimensions that give us maximum area are length, right, which was this L was 50 feet. And if you recall from earlier, the width is 100 minus L. 100 minus 50 is 50, so the width is 50 as well. Right, and the maximum area is that 2,500 square feet. So the picture I drew here with the 50 by 50 rectangle, the square, this is the rectangle that has the largest area possible when I'm only given 200 feet of fencing. Alright, so that was a lot, I know, but every single problem I'm going to do is like this, where you'll be given some information and you're going to be asked to maximize or minimize some quantity. Maximize area, minimize cost, maximize profit, whatever. And your eventual goal is to use the information in some sort of substitution to get the quantity you're maximizing or minimizing, like the area here, to be a quadratic function of a single variable. And then you're going to use the graph of that quadratic function, right, all the stuff you know about quadratic functions, to find that maximum or minimum value and answer whatever questions they have after that. Alright, so let's see this again. Alright, not this same problem, but a similar problem. Alright, so the next one I want to do is exercise 68 from the same section, same page. Alright, so that's this exercise here, and I'll read it first. Find the dimensions of the rectangular corral. So I'm making another rectangle, but this time it's not just a big rectangle, it's split into 3 pens of the same size, right? So find the dimensions of the rectangular corral producing the greatest enclosed area. So once again, we're maximizing area. So I would like to get area to be a quadratic function of a single variable. All right, we'll make some substitutions to make that happen. Split into 3 pens of the same size, and you're only given 500 feet of fencing. All right. So again, I'll make sure this information's still up there. So here's the thing that's happening now. Right now I'm making a rectangle, a corral, but it's broken up into 3 pens, all the same size. All right, pen 1, pen 2, pen 3, of all the same size. And all these little segments I drew, all the black lines, add up to 500 feet. All right, we only have 500 feet of fencing. All right, so once again, I'm going to call some things. Let's say the length of the rectangle, or the width if you want to call this the width. Let's call this L again. And the width of the rectangle, again, I'll call that W. But this time there's not 2 W's, there are 4 W's. Right? Every single one of these vertical segments has a length of W feet. And then, this other side is also the length L. Right? So you have 2 L's and 4 W's. So 4W plus 2L adds up to the 500 feet of fencing. And if you notice, everything is a multiple of 2. So if I divide through by 2, that'll make these nicer, right? 2w plus L equals 250. This is the equation I'll use. And we're trying to maximize area. Right? We're trying to maximize the area. Now remember, area is length times width, L times W. All right, let me go back to let me make the paper bigger now. But I don't want this L times W. I want a function of one variable, not two variables. Well, that's where this is going to come in, right? If I solve this for L, we'd have L equals, 250 minus 2W, and then I substitute that for L, right? Replace L with this quantity 250 minus 2W. So now I have 250 minus 2W times W, and if you distribute the W, you can see now that area is a quadratic function of W. It would be negative 2W squared and then plus 250W, right? And I'm just putting it in highest to lowest power. I'm putting it in that general form. And if you want to make a little graph too, you can. Right now, this time the horizontal axis is widths, is values of W, and the vertical axis is area. And I'm going to graph this quadratic function. Now, in factored form, it's easy to see that when W is 0, there's no area. Right? Obviously, if there were no width, there'd be no rectangle. And if W were 125, right? 2 times 125 is 250. There'd be no area as well. And halfway between these two would be a 62.5. That's where the axis of symmetry is going to be. Let's see, right? If you go little a equals negative 2, so it's going to be a parabola opening down, have a maximum value. Little b is 250. The axis of symmetry would be at w equals negative 250 divided by negative 4, which reduces to 125 divided by 2, which is, like I said, 62.5. So a width of 62.5 feet. So this is 62.5 feet. This is 62.5 feet. This is 62.5 feet. That width is going to get me maximum area. Right? All four of these segment 62.5. All four of those are 62.5. And then what would be the length? Remember, length here is 250 minus 2 times W. 2 times 62.5 is 125. 250 minus 125 is length is 125. So 125 feet by 62.5 feet. That rectangle gives me maximum area. And what is that maximum area? Right, if I plug this in, you'd have a 125 times 125 over 2. That'd be whatever, right? They didn't ask us for the maximum area. All they want is what are the dimensions. But this will be 125 squared over 2, whatever that is, square feet. And if you want to punch that in the calculator, you can. Yeah. But yeah, the dimensions though, right? The length is 125 feet. The width is 62.5 feet. That will produce the largest area possible for this corral I'm trying to create with the 500 feet of fencing I was given. All right. Great. And again, if you want to find that maximum area, just plug in 62.5 for W and use a calculator or whatever. Okay. Next example. Again, same kind of setup. You're given information. You're asked to maximize or minimize something. And then you're going to use the information and some sort of substitution to express the quantity you're trying to maximize or minimize as a quadratic function of a single variable. And then use that quadratic function to answer whatever question they have. Alright, so moving on to exercise 70. Alright, so this is among all the pairs of numbers whose difference is 12, find the pair with the smallest product. And then what is that product? Right, so again, I'll pull it up so both you can see number 70 up top here. Right. So we're looking for two numbers. So I'll say let m be the larger number and n be the smaller number. And we're told that their difference is 12. So m minus n is 12. All right, their difference is 12. M minus n is 12. We're asked to find m and n with the smallest product, right? So minimize their product. All right, now their product, and now I have enough information to get out of here. All right, let's make the paper bigger. Now the product, I'll call P, is just m times n. All right, but once again, kind of like those area problems, you know, P is a function of two variables. I don't want two variables. I want a quadratic function with one variable. So that's where the information we were given comes in, right? The difference between these two is 12, so m is equal to 12 plus n, or n plus 12, right? And I substitute that for m, right? Replace m with n plus 12, or 12 plus n, same thing, times n, and then we get a quadratic function. So p equals n squared plus 12n, and I can graph this pretty easily. You know, 0 would be a n-intercept. You know, the horizontal axis represents values of n. The vertical axis is values of product, now p. Obviously, if n were 0, the product of these two numbers, no matter what you pick for m, would be 0. And if n were negative 12, you'd also get a product of 0. Right? Because if n were negative 12, then m would have to be 0, right? Because their difference is 12, positive 12, and m is the larger number. So one of those would be 0, the product would be 0. Halfway between these is negative 6, right? And if n were negative 6, m is positive 6, their product is negative 36. All right, if I plug in negative 6 to this, we get negative 36. That's the minimum product, the smallest product possible. There's your minimum product. So the product P is minimized. P is minimized when n equals negative 6, and if n equals negative 6, m must be 6, and m is positive 6, and their product, the minimum product between two numbers with a difference of 12, must be 6 times negative 6, negative 36, right? This is all the stuff they were asking for right here, right? Because, I mean, there are other numbers whose difference is 12, like 13 and 1, right? 13 and 1, but 13 times 1 is 13. That's not smaller than negative 36. You know, negative 4 and 9. Or not negative 4 and 9, those. Negative 4 and 8. Those have a difference of 12, right? Negative 4 and 8, and their product is negative 32. That's not lower than negative 36, right? These two numbers, negative 6 and positive 6, these are the pair of numbers whose difference is 12, and their product is as small as you're going to get for any pair of numbers whose difference is 12. But again, the same procedure was kind of happening here, right? You were given information, asked to maximize or minimize some quantity. Then using that information and some substitution, you express that quantity that you're asked to maximize or minimize as a quadratic function of a single variable, and then went from there. So 66, 68, 70, all pretty similar. Now my next example, you're just given a quadratic function, so this should be a little easier. Just going to use a calculator as all. 72. So you see a rocket is launched in the air. Its height in meters above sea level as a function of time in seconds is given by the following here. So the height at time t, right? The height in meters at time t in seconds is this quadratic function here, and all they're asking us to do is find the maximum height the rocket attains. And this is basically boiling down to vertex, right? So I'm just going to go back to the page here. We have h of t equals negative 4.9 times t squared plus 229t plus 234. And I just need to know, this is a quadratic function here in general form, at squared plus bt plus c. A is negative 4.9, so it's it's opening down, right? And it's something that's in the air, right? Something shot in the air, so it's going up and coming down. We just need to know how high it gets. Right? What's the output at the vertex? Little b would be 229, right? And so the axis of symmetry here is t equals, right, because the input's t, negative b over 2 times a, which would be negative 9.8, right? 2 times negative 4.9. And this will be positive something. All right, now I'm just going to go to my calculator, and I'm just going to go straight, now let's go to that Desmos calculator again. Let's get rid of this. And you know what, I'm just going to put in the function we were given. H of t equals negative 4.9 t squared plus 229t plus 234. All right, and here's there's eventually some problem. There it is, right? The rocket shot up, and it eventually reaches some highest point. Yikes. All right. Zoom out until I see something good. All right, eventually, there we go. Eventually reaches some highest point and then comes down. There's the path of it. Now see here it's at 23. Now they're rounding to 3 decimal places. 23.367 should be my axis of symmetry. T equals, I said it was 229 divided by 9.8. Yeah, see 23.3673, blah, 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 right? Rounded to 3 decimal places is 23.367. That's the t value of that vertex. And you see the highest value, the highest height in meters that this thing reaches is 2,909.561. And that's all I'm going to do, okay? Going back here, this is I'll say this is approximately 23.367, and I think it was in seconds. Yeah, it said time was in seconds, right? So this is seconds. So after this many seconds, the height of the rocket is approximately, according to that page there, it was 2,909.561 meters in the air. And that's what we were asked to do, right? Find how high it was at its highest point. Okay. Right, find the maximum height the rocket attains, 2,909.561 meters. Right, so yeah, use a calculator for that one, right? Lots of decimals and whatnot. All right. I guess I should write that this is the maximum height reached by the rocket, right? Okay. And I got just one final example. It's just the next even numbered exercise in that real world applications area. Exercise 74. Right. So here we have a soccer stadium holds 62,000 spectators with a ticket price of $11. The average attendance has been 26,000. When the price dropped to $9, the average attendance rose to 31,000. assuming that attendance is linearly related to ticket price, what ticket price would maximize revenue? So once again, I'll throw this up here. Now, revenue is just how much money is being brought in, right? So yeah, revenue is just money brought in by the soccer stadium, right? Money brought in. So for example, you know, when the ticket price is $11, they say the average attendance is 26,000 people, meaning the revenue in that case, on average, would just be, you know, you get $11 from each of these people, so 11 times 26,000, right? Now 26 times 11 is 286, so $286,000 in revenue is brought in when the ticket, on average, for the average game, $286,000 is brought in when the ticket price is $11, right? Another example of this, you know, when the ticket price is $9, they said, the average attendance was 31,000 people. So the average, I guess I should say the average revenue, right? So the average revenue brought in per game here when the ticket price is $9 is, you know, you get $9 from each of these 31,000 people each game. So each game they're averaging 9 times 31 is 279, so 279,000. So you see, when they were selling the tickets for $11, they were making, you know, more money per game on average than when they sold it for $9. But the attendance went up for $9, so there might be some sort of sweet spot, you know, in between $9 and $11, where they're going to get more attendance and more revenue at the same time. All right, so that should be enough to be able to answer their question. All right, to be able to build some equations, build some models. Now they told us that attendance is linear related. Attendance is linearly related to ticket price. So that means we should be able to write an equation like this. If I call ticket price X and average attendance Y, if I call the ticket price X coordinates and the average attendance Y coordinates, the slope of that line, right, it's a line, would be, you know, 31,000 minus 26,000. It's the change in output divided by the change in input, 9 minus 11. 31,000 minus 26,000 would be 5,000 divided by negative 2. This would be negative 2,500 for the slope. Right. And let's use the point 9, 31,000. So we got attendance equals, you know, negative 2,500 times ticket price plus something. Now, negative 2,500 times 9, let me just do this, be 22,500, I'm pretty sure. I'm just going to pull up a calculator. Let's do this here. So negative 2,500 times 9, and then plus what would be equal 31,000. So I need 31,000 minus this. So 53,500 for the y-intercept. And again, you should be able to write the equation of a line. So here's the relationship between attendance and ticket price. Right, the average attendance is negative 2,500 times the ticket price plus 53,500. Right. So using this and talking about revenue, right? Revenue, I'll call capital R, is going to be X times Y, right? It's the number of tickets sold, the ticket price times the number of tickets sold on average, right? Times the attendance. And then I make this substitution, and we get X times negative 2,500 X plus 53,500, and we get some sort of quadratic function in terms of X, right? We have R equals negative 2,500 X squared plus 53,500 X, and then I can use this to find the maximum revenue, or what they, well, all they asked though, they didn't ask for the maximum revenue, I don't think. Right? They just asked for how many, assuming that attendance is linear related to ticket price, what ticket price would maximize revenue? So they're just asking for the ticket price here. They're just asking for the X coordinate of the vertex here. Right? My X's represent ticket price. So what's the axis of symmetry? X equals, negative 53,500 divided by, and then 2 times this would be negative 5,000. Right, and then we cancel a couple zeros here. So 10.75, $10.75. Maybe 10 and 35/50ths. Right? Nope, 10.70. And just to double check, just to make absolutely certain. 53,500 divided by 5,000. Yeah, 1070. Right. So according to all that, this is the ticket price that they should charge to maximize revenue. So this is the ticket price they should charge. Ticket price needed to maximize revenue. Maximize the value of this R here. Maximize revenue. Alright, and that was a lot. Alright, you had to find the equation of a line there, showing the relationship between attendance and ticket price, and then you had to do the substitution into the revenue equation. But yeah, it's after that equation came up, after you found that linear equation, right, the rest of it was very similar to the first three examples that were done in this video. Alright, and if you wanted to find that, what is the maximum revenue, you plug in 10.7 to our revenue function here for X. Okay, a lot of stuff. But they all ended up, most of them ended up being the same. You were given, again, one more time through. You're given information. You are asked to maximize or minimize some quantity, right? Revenue, area, cost, profit, whatever, product. And then using that information and some sort of substitution, you ended up expressing the quantity you were trying to maximize or minimize as a quadratic function of a single variable, and then basically found the vertex of that. Right? Went from there, axis of symmetry, then you plugged in that value, found the maximum or minimum value there. All right. So yes, I know it was a lot, but I'm hoping that watching me go over these several examples here, and obviously doing some on your own, help you in some way when you're working on problems like this, finding the maximum or minimum value of a quadratic function on your own. And thank you very much for watching.